Hello everyone, welcome to lecture module 2 on Synchrophasor fundamentals. This is the second lecture in the series of lectures on Synchrophasor technology. I hope you have already watched the lecture module 1, which dealt with the motivation for Synchrophasor technology. So now I think this is the right time for us to learn about the Synchrophasor fundamentals. So let's see the historical developments of Synchrophasor technology, and let's see how Phasor became Synchrophasor. That means we are looking at the journey from Phasor to Synchrophasor. Now it turns out that the concept of phasors is not really new. It is an old one. It dates back to 1893 when Charles Steinmetz published a paper and he talked about the concept of phasors, and he said that any time varying quantity can be represented as a phasor quantity, which means it will have magnitude and an angle. Now this concept of phasors was extended in 1988 by Dr. Arun Phadke and Dr. James Thorpe at Virginia Tech, where they tried to estimate real-time phasor measurements and use the GPS satellite time signal as the time reference for calculating those phasors. And that was the birth of phasor measurement unit and Synchrophasor technology. So the first commercially available PMUs were manufactured by Macrodyne, and that was back in the early 1990s. And as of July 2014, there are more than 1300 PMUs that have been deployed in the US, and the journey is still on. So now let's look at the Synchrophasor definition and representation of Synchrophasors. So the first thing is the word Synchrophasor itself can be divided into two parts. One is synchronized and the other is phasor. So basically Synchrophasor is nothing but synchronized phasor. Now let's look a bit more into details of the definition of Synchrophasor. It turns out that if we have a sinusoidal waveform, we will have A, which is representing the RMS value, which becomes the magnitude of the phasor. And then we have an angle, which is the phi, which is basically the angular difference between the peak of the waveform and the time reference t equal to 0. Now the question is, where does this time reference come from? It comes from the 1 pps or 1 pulse per second signal from the GPS satellites. That is what provides the time synchronization to these measurements. So if you want to convert this into phasor form, it will look something like this: A at an angle phi. Now we provide a time stamp to it and it converts to a synchrophasor. Now let's look at the representation of a synchrophasor. So as we mentioned that the synchrophasor is A at an angle phi, which means it can be written in two different formats. One is basically the polar form, like I mentioned, A at an angle phi. The other one is in the rectangular form, which is A real plus J times A imaginary. Now it turns out that both these formats are acceptable for Synchrophasor data streaming. Now let's look into what a phasor measurement unit is and what a phasor data concentrator is. So the question is, what is a PMU? So according to the IEEE C37.118 standard, it is a device that produces synchrophasors. So synchrophasors can mean voltage phasor, current phasors, which are time synchronized or time stamped, and it also produces frequency, rate of change of frequency, which we call the rock-off. These are estimated, and for the estimation we need the voltage and current signals, which are the analog signals which we can get from the CTs and PTs, and then we also need a time synchronizing signal which we can get from the GPS satellites through the GPS clock. Now the next question is, what is inside a PMU that enables us to get these estimates? And what are the different quantities that the PMU can estimate or measure. So in this figure we can see that from the CDs and PTs we can get the current and the voltage signals, the analog signals, which come inside the PMU, and they are sampled at a particular frequency, which can be, let's say, 12 samples per cycle or maybe more. Now these samples are put into the DFT or discrete Fourier transform block inside the PMU, and we extract the samples for the fundamental frequency component, which is the 60 Hertz for the US systems. And from that we try to estimate, using the different estimation algorithms, the different quantities like the voltage and current phasors, which are basically three-phase, and then voltage and current sequence components, frequency, rate of change of frequency or the rock-off, and the circuit breaker status. Now these quantities which are estimated by the PMU comes at a particular rate, which is called the reporting rate. And it turns out that for 50 Hertz system this reporting rate is a bit different for the 60 Hertz system. And in the 60 Hertz system, for example, like in the US, the reporting rates at that means the frequency at which the data is being output by the PMUs can vary from 10 frames per second to 12 frames per second to 15 frames per second or 20 frames per second or 30 frames per second or even 60 frames a second. So that's how fast the data can be obtained from the PMU. Now, what is the benefit of this? If we are getting the estimates of the states of the system, like voltage magnitudes and voltage angles, at this high frequency, then we can actually get to monitor the dynamics of the power system in a much better way. So that is one of the most important advantages of having Synchrophasor technology and getting the measurements from the PMUs at this fast rate. Now let's look at how the PMUs can be integrated in the power system measurement infrastructure. So we can see that we have the figure which shows the current transformers and the potential transformers which are there in the substations. Now these send the current and voltage signals to the PMU, which is placed at the output of these CDs and PTs. The PMU gets these voltage and current signals, and it also gets the time synchronizing or the reference time signal from the global positioning satellite through the GPS antenna. And that is how it can be fitted in this existing power system infrastructure to generate those quantities like I mentioned in my previous slides. For example, the voltage phasor, the current phasors, the sequence components of voltages and currents, the frequency, the rate of change of frequency, and it can also estimate the breaker status. Now let's look at the time synchronization part of the PMUs. This is a very important part. How do the PMUs get time synchronized? So we see in this particular figure that we have the Earth which is surrounded by 32 functional GPS satellites. Let's say we have a substation 1 which has the GPS antenna which is giving the time signal from the satellites to the GPS clock, which is giving the IRIG-B format time signals to the PMU. A similar architecture is present, let's say, at a substation 2, which is geographically quite distant from substation 1. Now it is necessary for the GPS antenna to sync or connect with at least 4 out of the 32 functional GPS satellites. So you can see this is how it locks with 4 satellites, and that is the result of a proper time synchronization. Once they are properly time synchronized, you can see that substation 1 will estimate the magnitude and the phasor from the waveform as A1 at an angle phi 1. And like I mentioned before, phi 1 is basically the angular difference between the peak of that waveform and the reference time. Similarly, the substation 2 PMU will estimate the phasor as A2 at an angle phi 2. Now if we know A1 at an angle phi 1 at substation 1 and A2 at an angle phi 2 at substation 2, we can easily calculate the angular separation or the angular difference between these two substations if they are connected. So like I mentioned in the previous video, when I talked about the motivation of synchrophasor technology, I had mentioned that angular separation is a very good indicator of the stress in the system. And you can see that this is the technology, the synchrophasor technology, that provides us the angular separation at the local substation level itself. This is how powerful this tool is. This is how powerful synchrophasor technology is. And we need to make use of all these important advantages. Now let's look at what are the different performance classes of PMUs. So we can say that there are two basic performance classes of PMUs. The first is the P class PMU, and the second, like I will mention after this, is the M class PMU. Now let's see what are the different important features of the P class PMU. The first thing is, this is intended for those applications which require real fast response. And if we really need those fast kind of response, we have a lot of time constraint. So we do not need explicit anti-aliasing filter in this particular type of PMU. That saves a bit of time. And then we also shorten the window length, which is used for estimating the phasor quantities. Now let's look at the M class PMU. Now this is basically intended for those applications where the applications are affected by aliased signals. That means we are required to have some anti-aliasing filtering in this kind of a PMU. Not only is this an important feature of the M class PMU, but the other important feature is that it uses a relatively longer window length for estimating the phasor. That means M class PMUs will be more accurate than P class PMUs over a wider range. So that is the basic classification of the performance classes of the PMUs. Now let's look at another important component in the synchrophasor technology infrastructure, that is a phasor data concentrator, a PDC. Now what is a PDC? A PDC, according to the IEEE standard, is basically a functional unit which collects the phasor data and all the other discrete event data from the different PMUs or maybe some lower level PDCs and sends the data to the higher level PDCs or maybe to the applications running the EMS in the control center. And you can see the figure, it shows that the PMUs at the lower level collect the data from the substation, and then there will be a few number of PMUs giving the data for archival into the phasor data concentrator, maybe at a higher level substation at a higher level voltage. Now these PDCs are there in different higher level voltage substations, and they are collecting the data from the PMUs and archiving it and storing it, and also sending the data either to higher level PDCs or maybe directly to the central control center for the EMS applications. So that is the figure that shows this kind of an architecture. Now, having talked about the synchrophasor technology infrastructure, it is important to show you this interesting figure. We can see that the CTs and PTs are getting the current and the voltage analog signals, and all these signals are sent to the PMUs which are located in the substations like I had mentioned. Now these are sending the data, the synchrophasor data, through Ethernet to the different PDCs or the phasor data concentrator, which can be at the higher level substations or maybe the regional monitoring center, and then using again the Ethernet or VPN, we can send the data from these PDCs to higher level PDCs or the EMS applications, and the EMS applications can be of several types. The state estimation algorithm in the EMS might need Synchrophasor data. There can be stability algorithms as well running in the EMS which will need Synchrophasor data to see if the system is stable or not, or if some proper control actions need to be taken to make it the way the operators want it to be. So this is the typical Synchrophasor technology infrastructure. Now let's look into one of the important topics in this module, which is the criteria for PMU installation in the transmission system. So the PMU installation actually has been separated into different plans. So the first plan is till 2014, and that says that all the 500 kV buses or substations, or the substations mostly which are above 200 kV, most of those substations should have PMUs installed in them. Not only this, but major transmission interconnections and all the interfaces also need to have the PMUs, so that we can keep monitoring all the dynamics happening at those locations in the power system at a much efficient manner. Then it also says that we need to have the PMUs at those key generating plants which have generation above 500 megawatt. And then it is also required that the major load centers which consume a lot of power also need to have PMUs for continuous monitoring of the electrical parameters. And then we know that the renewable penetration that is happening now, they are putting a lot of dynamics into the system. So it is very important that we monitor those large wind generators of the solar farms along with the storage locations with the PMUs, so that we can monitor the dynamics in a much better way. Now that was the plan till 2014. There's a plan for 2019 as well, and that is to cover all the 500 kV level substations along with all the 200 kV level substations with the PMUs, and maybe even have some PMUs in the important regions in the distribution network. That is a big step. And then there is some more research that is going on, and that's probably a long-term plan for PMU deployment, and that is optimal PMU placement in such a way that you can make the entire power system 100% observable using PMUs only. That would be the time when we can reap a lot of benefits from the Synchrophasor technology. That is the time when we can realize how powerful this technology is, if we can get our entire system covered with PMUs. Well, we are progressing towards that. Hopefully this time comes soon in the future. So now let's see the present deployment status of PMUs and PDCs in the US power systems. So if you see this map, you can see that the blue dots here, they show the location of the PMUs in the different power systems, and the yellow stars, they show the locations of the PDCs in the power systems. So it turns out that as of July 2014, there are more than 1300 PMUs that have been deployed in the US power systems. And if you see this slide, you can see the exact locations, the different utilities and the ISOs that have PMUs. And as of the same time, there are more than 165 PDCs that have been deployed in the US power systems. So even though 1300 PMUs have been deployed, 165 PDCs have been deployed, probably in the future there will be more of these kind of devices, and hence the journey will still continue. So now let's end this lecture by showing you a comparison of SCADA and Synchrophasor technologies. If you see this table, it shows that in SCADA technology, the universal time synchronization is not available. However, in Synchrophasor technology, universal time synchronization is available. Again, in SCADA technology, the phase angles, they cannot be estimated locally. I mean, at the substation levels, they cannot be estimated. However, on the other hand, in synchrophasor technology, because the reference time signal is available, the phasor angles can be estimated locally at the substation level. And lastly, the reporting rate for SCADA is once in 4 to 6 seconds, which is pretty slower than the reporting rate of the synchrophasor technology, which can be either 10 frames a second or 12 or 15 or 20 or 30 or even 60 frames per second. So that's really fast. Now, this is the synchrophasor technology which has the capability of providing the wide area monitoring of the system in a time synchronized manner. That's one of the most powerful aspects of synchrophasor technology. And the other thing is, being so fast, the reporting rate, we can monitor or capture all the dynamics of the system in a very efficient manner. And lastly, because the synchrophasor technology can provide us these kind of benefits, that enables much more efficient monitoring of the system and hence faster control of the power system. It is this technology which has the power of most probably even preventing blackouts. So in the future, with more deployment of PMUs and PDCs, our power system can become even more secure and reliable. That is the power of synchrophasor technology. So well, this was everything in lecture module 2. Hopefully you enjoyed the lecture. I'll meet you again in the lecture module 3. Thank you.